So in part one of matrices, we discussed about some basic definitions of a matrix. In this part, we are going to talk about some of the operators, some of the calculations about matrices. So for example, how to find the transpose of a matrix, or how to calculate determinant of a matrix, and why they are useful. So the goals of this part are first, to understand how to transpose a matrix, the definition of identity matrix, and determinant. We also will talk about some properties of determinant before talking about invertibility and finding an inverse of a given matrix. All right, so given a matrix A of dimension m by n, its transpose is represented by A to power t, or A transpose, and is a matrix of dimension n by m. So as you can see here is m by n, but the transpose is n by n. And what we have for each entry of the transpose matrix, so A transpose ij is equal to AJI. Let's take a look at one example. So this is our matrix A. So A11 is equal to 0. A12 is equal to 4. A21 is equal to 7. A22 is equal to 0. A31 is equal to 3. And A32 is equal to 1. So now we want to find the elements of the A transpose matrix. So A transpose 1, 1 is equal to A11, because if we change the location of these two, it's going to be the same. A transpose 1, 2 is going to be A21, which is nothing but 7. A transpose 1, 3 is A31, which is nothing but 3. So let's take a look at these three elements. As you can see, 3, 7, 0. 3, 7, 0. 0, 7, 3. And we have the same thing for the second row of A transpose. So A transpose 2, 1 is equal to A12. What is A12? It's 4. A transpose 2, 2 is the same as A22, which is 0. And A transpose 2, 3 is A32, which is equal to 1. Again, if you look at what we have here, 4, 0, and 1. This is how we find the A transpose. Another simple way is just to visually say, all right, I have this column here. I transpose the column, and I have this row. I have the second column here. I transpose it, and I have it here. So the same properties that we talked about for transposition of vectors apply to matrices. For example, if you have matrix A transpose is equal to A. And a matrix is called symmetric if A is equal to A transpose. Let's take a look at one example. All right. So just by looking at this matrix, you can see that it's symmetric. So these two elements are the same. 3 and 3 are the same. 4 and 4 are the same. But now let's try to find the transpose of this matrix. Let's call this matrix A. What is A transpose? As I said, visually, you can just consider columns of this matrix as rows of the transpose matrix. 1, 2, 3. 2, 1, 4. 3, 4, 1. All right. As you can see, these two matrices are identical. So A transpose is equal to A. So this is a symmetric matrix. The next definition that we have here is identity matrix. The identity matrix is denoted by I. It's a square matrix with the diagonal elements being 1 and all other elements being 0. For example, the identity matrix of size 2 is 1, 0, 0, 1. The identity matrix of size 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Given any matrix B with dimension n multiplied by m, B multiplied by I of n dimensional is equal to I of m dimensional multiplied by B and is equal to B. All right. So let's define B to be 1, 2, 3, minus 1, 0, 1. All right. So what it says B, which is here, 3 by 2. So we can multiply matrix B by the identity matrix from the right side with the proper dimension is equal to identity matrix multiplied by B is equal to B. And something which I want to correct here, this should be m by n. Because here we have B 3 by 2 and this I should be 2 by 2. So this is n, this is n. So this is In, which is equal to I2. And this is I3. All right. So this is the definition of identity matrix. Now let's get into the determinant. Determinant of a square matrix, let's say matrix A, is denoted by various symbols. So we can show it by determinant of A or determinant of A. Also, in some notations, they use determinant of A or determinant of A without parentheses. So any of these notations is acceptable to show determinant. But what is determinant? It's a numeric quantity, it's a scalar using the entries of the matrix A. So one common use of determinant is to find whether a system of equations, which is represented by a square matrix, has a unique solution or not. So if the determinant is equal to 0, in that case, the system doesn't have a unique solution. So we are going to explore this further later. But first, let's take a look at specific examples, special cases of determinant before talking about the general rule for finding determinant. So we start with determinant of 2 by 2 matrix. All right, so let's define matrix A to be A, B, C, D. Determinant of A is equal to A multiplied by D minus B multiplied by C. All right, example, A is equal to 2 minus 4, 3, 1. So determinant of matrix A, or another symbol, determinant of matrix A is equal to 2 multiplied by 1 minus 4 multiplied by 3, which is nothing but 2 plus 12 equal to 14. This is one example of determinant for 2 by 2 matrix. Another example is 3 by 3. So determinant of 3 by 3 matrix. So for the 3 by 3 matrix, we are going to use our definition for 2 by 2 matrix. How do we do that? So we have A, B, C, D, E, F, G, H, I. All right. So we start with the first entry at the top left, entry A. We remove all elements in the same row and column as A, and we say A multiplied by determinant of the rest of the matrix, E, F, H, I. then minus B. Now we have B. Again, we remove the row and column which are at the same row and column as B, and we use the rest of D, F, G, I plus C. Again, we remove elements at the same row and column as C and keep the rest of it, D, E, G, H. So this is the determinant of our 3 by 3 matrix. And now you already know the definition of 2 by 2 determinant. So determinant of this is going to be E multiplied by I minus H multiplied by F, or D multiplied by I minus G multiplied by F, or DH minus EG. Let's take a look at the example for 3 by 3 matrix determinant for clarification. All right. So I want to find determinant of matrix A, defined as 1, 0, minus 2, 3, 2, 0, 4, minus 1, 1. Right. Determinant of A is going to be, so it starts from the first element, 1 multiplied by determinant of this matrix, 2, 0, minus 1, 1, minus 0, which is this 0. Now we remove this. We are going to have this 2 multiplied by 3, 4, 0, 1, plus, now we have the last element, minus 2. We remove this, multiplied by determinant of this block, 3, 2, 4, minus 1. All right. Now let's expand those determinants. So it's equal to 1 multiplied by 2 multiplied by 1 minus 0 multiplied by minus 1, which is 2. Minus 0 multiplied by 3 multiplied by 1, which is 3, minus 0. Plus minus 2 multiplied by 3 multiplied by minus 1, which is minus 3. Minus 2 multiplied by 4, minus 8. It's going to be 2 minus 0, minus 2 multiplied by minus 11, 2 plus 22, which is 24. So this is how we find the determinant for 2 by 2 matrix and 3 by 3 matrix. Now let's take a look at the general rule, how we can find the determinant for an n by n square matrix in general. All right, before talking about the n by n matrix determinant, first let's explain how we represent a matrix again. So if we have matrix A, each element of matrix A is represented as Aij. So A11, A12, and so on, A1n, A21, A22, A2n, AN1, AN. So this is an n by n matrix. So Aij is element of row I and column J of matrix A. So keep this in mind. We want to define two new factors before talking about the determinant of n by n square matrix, right? So minor. Given a square matrix A, so we have a square matrix A. The minor of element Aij of matrix A is represented by Mij. So M sub ij is the minor corresponding to element ij. And what's Mij? It's the determinant of the matrix that is created by removing the i's row and j's column of the original matrix. If you remember, for the 3 by 3 matrix, A, B, C, D, E, F, G, H, I. What I was saying for element A, remove the corresponding row and column of matrix A, and then find the determinant for the rest of it. So this is called the minor. All right, so let's write the definition of minor. Minor of element Aij represented by Mij is the determinant of matrix formed by removing row I and column J of matrix A. All right. The next definition is cofactor. So cofactor of element Aij of that matrix. Again, it's represented by C sub ij is, this is how we calculate, -1 to power I plus j multiplied by Mij. All right. So both minor and cofactor will be used to find the determinant of the matrix. So this is cofactor, and minor is already defined. So keep these two in mind. We have Cij, which is cofactor, Mij, which is minor. All right. So minor is M sub ij, and cofactor is C sub ij, which is nothing but -1 to power I plus j Mij. All right. Now we want to use this to create a step-by-step process to find determinant of an n by n matrix. All right. Step 1. Step 1. Choose an arbitrary row or column of matrix A. Usually we go with the first row. I mean, that's what we did for the 3 by 3 matrix. So if I want to show this for the 3 by 3 matrix, A, B, C, D, E, F, G, H, I. So we started in the 3 by 3 example, we started with the first row. All right. Step 2. Multiply each element of the chosen row or column. In our scenario, each element of this row by the elements cofactor. What does that mean? So for that row, find Aij multiplied by Cij for all of the elements in that row. In our case, it's going to be A multiplied by cofactor of A, B multiplied by cofactor of B, and C multiplied by cofactor of C. All right. So let's find the cofactor of A in our example. Cofactor of A is, first we have to remove the row and column that are corresponding to A, and then use the rest of it. So it's going to be determinant of E, F, H, I. But if you recall, for cofactor, we also have -1 to power I plus j. So A is the first row and first column. So 1 plus 1. Cofactor of B. For B, we have to remove this row, this column, and this row. So it's going to be D, G, F, I. Determinant of D, G, F, I. Multiplied by -1 to power 1 plus 2. And for C, we are going to have D, E, G, H. -1 to power 1 plus 3. Determinant of D, E, G, H. All right. Sum of the integers, step 3. Sum of the cofactor products from the chosen, again, row or column. So whatever you choose with that one. So that gives you the determinant. So determinant is basically, so determinant of matrix A is going to be sum of the elements in the chosen row or column multiplied by their cofactors. So first, we multiply each element by its cofactor, and then we sum them up, and it gives us the determinant. So let me clear here and go over the 3x3 example one more time. So let's say we have matrix A, B, C, D, E, F, G, H, I. All right. So element A is element A11. So I is equal to 1, J is equal to 1. So I'm going to choose the first row. Element B is A12, so I is equal to 1, J is equal to 2. Element C is A13, so I is equal to 1, J is equal to 3. All right, now let's find the cofactors for each of them. Cofactor for A is going to be determined by remove the first row and first column of A. And then find the determinant, and then multiply by -1 to power I plus j. All right. So if you remove the first row and first column, what we have is E, F, H, I. So determinant of this multiplied by -1 to power I plus j. I is 1, j is 1. So -1 to power 2 is 1. It's going to be E, F, E, F, H, I. All right, this is for cofactor of A. So let me have cofactor of B. For cofactor of B, the same, -1 to power I plus j. I is 1, j is 2. Multiplied by, we remove the row and column corresponding to B. We are going to have D, F, G, I. But -1 to power 3 is -1. D, F, G, I. And the last one, cofactor of element C, -1 to power I plus j, 1 plus 3. Determinant of, we remove these two, D, E, G, H, which is equal to 1 multiplied by D, E, G, H, or determinant of D, E, G, H. All right, Now we have these three cofactors for A, for B, and for C. Determinant of matrix A is equal to the first element, A, multiplied by its cofactor, EFHI, plus B multiplied by its cofactor. It has a negative one here, so minus B DFGI, plus C multiplied by its cofactor, DEGH. This is exactly the definition that we had in the previous slides for determinant of 3 by 3 matrix, which was here, right here. All right. So I explained this to give you an idea about the about the determinant of 2 by 2 matrix, 3 by 3 matrix, and n by n matrix in general. But the question is, what do we do if we have larger matrices? So in Python, you can use Applied Linear Algebra module to find determinant. So simply, you can use this function, which is available in Python, to find the determinant of a given matrix. In MATLAB, if you define matrix A, you can use the command det parentheses A to find the determinant of the matrix. So these are two ways of finding the determinant in Python and MATLAB. All right. The next thing that we want to talk about is properties of determinant. Given two matrices A and B that both have dimensions n by n and given a scalar alpha, what we have is determinant of I is equal to 1, where I is the identity matrix. So if you want to find the determinant of identity matrix, no matter what's the dimension of it, it's going to be 1. Determinant of A transpose and A are equal. Determinant of A inverse is equal to 1 divided by determinant of A. I'm going to talk about A inverse soon in the next slide. Determinant of multiplication of two matrices is equal to determinant of each of them multiplied together. Determinant of a scalar alpha multiplied by matrix A is equal to alpha to power n determinant of A. This is also another thing that you have to consider. All right, invertibility. If you are given a square matrix A, it's invertible, non-singular, or non-degenerate if there exists a square matrix B such that A multiplied by B is equal to B multiplied by A is equal to I. In this case, we show B as A inverse. So we say B is A inverse. This is how we read it. And if it does not exist, then we say A is a degenerate or singular matrix. So how can we determine whether matrix A is invertible or not? So we can easily determine that by finding its determinant. If determinant of a matrix is equal to 0, then the matrix is singular. Otherwise, the matrix is non-singular and has an inverse. There are some properties for matrix A, which is a square matrix, and alpha, which is a non-zero scalar. So inverse of A is equal to A. The next property, if we multiply a scalar alpha by A and find the inverse, it's equal to finding inverse of alpha, which is 1 divided by alpha, inverse of A, or 1 over alpha, inverse of A. And another thing, inverse of transpose of A, so A transpose inverse is equal to A inverse transpose. Another interesting property that we talked about in the previous slide was determinant of A inverse is equal to 1 divided by determinant of A. All right. For the inverse, because it's more complicated than finding the determinant, and usually we do it during our code, during the programs that we are using, I'm going to introduce the packages for Python and also the command for MATLAB to find it. So in Python, you can use NumPy linear algebra module. So this is the command that gives you the inverse of a matrix. And in MATLAB, you can use the command inverse A to find the inverse of given matrix A. So this was part 2 of matrices. We talked about the identity matrix. Then we talked about how to find determinant for 2x2 matrices, 3x3 matrices, and in general, n by n square matrices. We also talked about how to find transpose of a matrix. And finally, we talked about how to find inverse of matrix A using MATLAB and Python. A small point that I want to mention here is determinant of 1 by 1 matrix is just itself. So if matrix A is equal to 2, then determinant of A is 2. Or if matrix A is minus 12, determinant of A is equal to 12. That was all for part 2 of matrices.